Okay, thank you very much, Sergey. And thanks to the organizers for inviting me to give this talk on coupled data assimilation, or actually towards coupled data assimilation at our center. And I'd like to first acknowledge my co-authors. So Sergey is the first, and Alan and Alex also, all from Environment Canada. We work here in, as Veronique mentioned, nearby in Dorval. I'm a research scientist there, working mostly on data assimilation applications for numerical weather prediction, but also for sea ice and ocean, so SST as well with Sergey. Okay, so first of all, just the contents of my talk. So I'm going to be talking about our recent work and also future plans working towards fully coupled data assimilation. So first I'll give a quick overview of our current NWP systems and the role that SST and also sea ice analyses play within those systems. And then I'll briefly mention like why we would consider moving towards strongly coupled data assimilation. And the increasing use of what we call MIDAS, which is the data assimilation software we've developed at Environment Canada for Earth system data assimilation. And the general idea behind that is by first using the same software and assimilation algorithms for each Earth system component, that'll facilitate moving incrementally towards coupled assimilation. And then I'll mention at least one role that SST analyses play in the current NWP assimilation system and talk about our sea ice analysis a bit. And then briefly talk about the SST analysis that we've recently implemented in MIDAS software. And this is as a first step towards full 3D ocean assimilation using a local ensemble transform Kalman filter, or LETKF. And then I'll finish up by talking about the incremental next steps moving towards strongly coupled assimilation. So this figure essentially summarizes our main global and regional NWP systems. So we can see on the top, oops, sure. Yeah, I don't know if you can see that pointer. So along the top, we have the two main global assimilation systems. On the left, deterministic, and on the right, ensemble. So we call these the global deterministic prediction system, global ensemble prediction system, and on the bottom, we have the regional systems, both deterministic and ensemble. And a feature of our system, well, as was already mentioned, I think by Veronique, our main forecasts are coupled, so including our global NWP forecasts, they're coupled to the ocean and sea ice components, but they're initialized using uncoupled data assimilation systems currently. All of our assimilation systems are based on, for the weather, for the atmosphere, rely heavily on ensemble covariances. So in this case, the global ensemble system essentially provides ensembles for specifying the background error covariances for all the other systems. So that's because we use four-dimensional ensemble variational assimilation for deterministic, and it's also one of the components within the ensemble data assimilation system combined with the LETKF algorithm. And we've developed in-house SST and sea ice analysis systems that provide their analyses to all the other systems, including these NWP systems. And I'll show on the next slide how all these main global data assimilation systems interact with each other. There's a lot of arrows here, so that really highlights that these so-called uncoupled systems are really, coupled in a sort of pseudo-coupled way, where we need to account for the connections between all these different systems. And you can see with all the red arrows, this is how the current SST analysis system feeds into the ice analysis system, the atmospheric system, and the ocean system. And this slide essentially summarizes what all those arrows were on the previous slide. I won't go through all of them, but just to highlight for the SST analysis, it's used within the sea ice system for observation quality control, for removing spurious non-zero ice concentration retrievals. Also, of course, as a lower boundary condition, for the background atmospheric forecast within the NWP system, and it's also assimilated or within the 3D ocean assimilation system. Okay, so if we move in the future towards a fully coupled data assimilation system, the one benefit is the figure gets much more simple. So essentially, instead of having multiple models, we're using the coupled model within the assimilation cycle, and instead of having multiple separate data assimilation systems, we'd have a single coupled data assimilation system. And as I mentioned, because our systems rely a lot on ensemble covariances, essentially the coupled model would provide coupled ensembles that would then be used within the coupled data assimilation system. So there's some advantages. As I mentioned, it reduces the number of systems that we would need, and it more easily allows us to include links between the different Earth system components. The observations assimilated in one component could immediately provide corrections to other components through the coupled ensemble covariances, and this should help ensuring consistency between the Earth system components at the initial time. And the observations that are directly related to multiple Earth system components, so near the interfaces between the components, could be assimilated in a more optimal way. There are also some disadvantages. So this represents a very big change relative to the current operational systems. And working at an operational NWP center, it's certainly much easier to implement big changes as a series of smaller incremental changes instead of trying to change many things at once. And also it really decreases the flexibility that we have currently in the system, since all the components would need to share, to be fully coupled, share a common data assimilation time window, same observation cutoff time, which is important for operational systems. They'd have to run in the same time slot on the computer, and to use the coupled covariances within a single coupled assimilation system, they would have to use the same assimilation software. So to move in this direction, we've developed our own data assimilation software, which is quite flexible. It's called MIDAS, the Modular and Integrated Data Assimilation System. So the idea is it's a unified assimilation software framework, both for research and operational use at Environment Canada. We use it now for all the operational NWP systems, and as of today, also for the operational sea ice analysis. So the objective of developing this software is really to avoid redundant work within the organization. So people working on very similar data assimilation problems can work together, developing a single software. And it will also, as I mentioned, facilitate a transition towards fully coupled data assimilation in the future. So I won't go through all the details here, but the idea is it currently has quite a bit of functionality, including the variational and ensemble data assimilation algorithms used by the NWP systems, and also recently the both sea ice and SST analysis capability is included using a 2D VAR approach. And by having these capabilities within MIDAS, it makes it quite straightforward now to test ocean and sea ice applications using the other assimilation algorithms within MIDAS, so the LETKF and 4D ENVAR. And I'll also mention later in the talk about some limited 3D ocean assimilation capabilities that we've implemented into MIDAS. So just to give an overview, MIDAS is essentially a grouping of about 20 programs, separate Fortran programs that use a collection of more than 100 Fortran modules that are all coded in a reasonably general way, so that the same modules, same code, and assimilation algorithms can be used for multiple applications for sea ice, for SST, for the atmosphere. So now I'll talk a little bit about the role that SST plays in the current NWP assimilation system. So one example of the need is the need for surface skin temperature over the oceans. So an important observation over the ocean for the atmosphere are these surface-sensitive, both microwave and infrared satellite radiance observations. But the challenge of assimilating these observations is that they're sensitive both to the atmosphere and the skin temperature. So currently we use the SST analysis as this to provide the skin temperature information, but it's believed it's not always accurate enough for getting the most information out of these satellite observations. The problem is that any errors within the skin temperature will result in errors from it will impose errors in the air temperature analysis. So this is something we want to avoid. So currently we use the SST analysis only as the background state within the assimilation system, and then the SST is updated within the NWP assimilation system, along with the air temperature and humidity, et cetera. But like is done at some other centers, we don't actually use this updated SST produced by the NWP system for any other purpose. It's just there to help us make better use of these surface sensitive observations. So it's important in this case, which we don't do currently, but to more appropriately differentiate between different types of SST, whereas the satellite observations that we assimilate in the NWP system are sensitive to the ocean temperature very close to the surface, but typically, as in the case of our system, where we produce a daily SST analysis, that analysis is more trying to get at the foundation SST, which is the ocean temperature at a deeper level. So there's been studies where they've shown that using a model to relate skin temperature to the foundation SST can help in the assimilation of these observations. As an example here, I'm just showing in our current system the SST increments produced by the NWP system at a single time. So just look at the areas over the ocean. Here on the right, we have the increments of the skin temperature produced by assimilating all the atmospheric observations. And in our current system, because we don't have a coupled ensemble data assimilation system at this point, and we only have a single SST analysis. So every 6 hours in the atmospheric data assimilation cycle, the sea surface temperature is reset to the same SST analysis for every member. So there isn't enough ensemble spread for the skin temperature when we do the assimilation. So this results in near zero increments over much of the ocean, and we only have more realistic size increments in very limited regions. Okay, so now I'm going to talk a little bit about the sea ice analysis system that we've developed at Environment Canada. So as I mentioned, well, as I showed in one of the previous plots, we do the sea ice concentration analysis every 6 hours. It's done both on a regional and global grids. It's used both in the NWP and ocean prediction systems, and it's based on a 2D VAR approach with horizontal background error correlations modeled using a diffusion operator. Also, we produce analysis error estimates using a simple OI approach, optimal interpolation approach, to provide a measure of uncertainty. So I think that's quite important, and it's used in different ways to really add value to the sea ice analysis. We've recently migrated the sea ice analysis, ice concentration analysis into our MIDAS software. And so this allowed us to make use of a lot of the existing Fortran modules. And we're also in the process of developing both ice type and ice thickness analyses for various applications. So an interesting aspect of our sea ice assimilation system is that we assimilate a wide range of of observations that have very different spatial resolution, as shown on this slide here. So everything from the SSMIS and ASCAT observations with satellite footprint sizes over 50 kilometers, AMSR2, the manually derived CIS, the ice charts from the Canadian Ice Service, which is quite a bit higher resolution, closer to the resolution of our analysis grid, and then even higher resolution observations that we recently started assimilating from RCM. So that's the RadarSat Constellation mission, a SAR sensor on a constellation of satellites. And we can compare that to the spatial resolution of the regional and global analysis. So what we do to be able to combine these observations with very different spatial scales is to use an observation operator that aggregates all the analysis grid points that fall within each observation footprint. And this allows us to assimilate low resolution and high resolution observations simultaneously. And the low resolution observations will only act to constrain the large scales and allow the higher resolution observations to be kind of unconstrained when fitting the smaller scales. So I think it's quite a useful approach. And in theory, given the interest of GRIST for SST and going to finer scales, I think it's an interesting approach that could be applied also for SST. So as I mentioned, we recently started assimilating this RCM SAR observations. So these are very high resolution observations. This is a project by Alex Komarov, who developed the algorithm over several years. And we can see here on the left, we have a SAR image, and then in the middle, we have a retrieval of ice concentration from that SAR image. And on the right, we have a comparison based on about 4,000 RCM images over about a 1 year period, showing a very good consistency between the ice concentration obtained from the SAR data versus from image analyses. And this I won't go into detail here. It describes the approach. It's essentially a multi-scale approach, trying to obtain ice, no ice retrievals at very fine scales and aggregating that information to slightly larger scales to obtain the ice concentration estimates, and always taking into account it's a probabilistic approach. So only attempting to perform these retrievals of ice information where the data unambiguously allows us to do so, and so this approach will return no value in areas essentially where we don't have high enough confidence, and that's important for data assimilation applications. And this shows the impact when we assimilate RCM observations, in addition to all the other observations we already assimilate in our ice analysis. And the plot shows the change in the proportion correct total when we compare our analyses against more or less independent IMS analyses that are produced by NOAA. And we can see that we have large changes, large improvements in red here. So up to 20% improvement in the percentage correct for ice versus no ice, mostly over small lakes, or you see over Canada and northern Canada. So this is because of the very high resolution. The sensor is able to see these lakes, whereas all the other observation types have trouble there. And also near coastlines and a little bit along the ice edge. So everywhere where you'd expect high resolution to bring a benefit, that's where we see improvements. This slide shows a little bit about a similar approach that Alex developed for distinguishing ice type from SAR data. So namely distinguishing first-year ice from multi-year ice. And as an example, we have on the left here an example of a single SAR image. And then in the middle, the retrieval for showing multi-year in red and first-year ice in red. And on the right, at the same time, a manual image analysis performed by the Canadian Ice Service showing the partial concentration of multi-year ice. And we can see pretty good agreement between the two. Of course, we have a lot finer level of detail when using SAR data compared to the manual analysis, which is really based on they come up with a set of polygons. So it would never be able to have this sort of pixel level detail that we can get using the SAR data directly. And here's an example of when we additionally use the RCM SAR data in addition to lower resolution observations from passive microwave and scatterometer data for estimating ice type. And we can see on the left here at the top is without the SAR data, and at the bottom's with the SAR data. And we can see in these black circles, we can see differences between the two. And again, it's areas where you would expect high resolution to help, to be a benefit. So in small bays here in the Arctic, and which is much more consistent with what we see in the Canadian Ice Service regional chart. Again, a manually obtained analysis of ice type. And we're also doing some work like some other centers in the world on an ice thickness analysis. So combining Cryosat-2 observations for the thicker ice with SMOS data for thinner ice using, again, a similar 2D VAR approach, so two-dimensional variational assimilation. And when we compare here the analysis we get for a particular day from results from our regional ice ocean prediction system, which currently doesn't use any ice thickness observations to constrain the thickness, we can see quite large differences. And when we compare both of them to independent ice bridge observations, we see that there could be quite a benefit using the ice thickness analysis to update the thickness in the model. Maybe not for all, currently not for all ranges of ice thickness, but within this particular range, which really covers a lot of the central Arctic, we think the analysis can bring an improvement to our current system. So now I'll switch to talking about SST, ocean, and coupled assimilation. So just very briefly, Sergey has a talk later in the session where he'll give a lot more detail on our new SST analysis system. So just to mention that, like what I talked about for the sea ice system, it's fully based on using the MIDAS software. It uses a similar 2D VAR approach with diffusion operator for the background error correlations. And we really see this as a first step, the ability to assimilate all the SST observations directly within MIDAS. It creates new possibilities related to coupled assimilation. So, and it also could reduce the need to even need a standalone SST analysis system, because we could now quite straightforward assimilate the SST observations in a MIDAS-based 3D ocean assimilation system, instead of like in our current system where we assimilate the SST analysis as if it's observations within the ocean assimilation system. But also we could assimilate these SST observations directly in the NWP assimilation system, in addition to all the existing atmospheric observations. Okay, so as I mentioned, so we've started doing this. Sergey has started doing this, exploring using MIDAS for 3D ocean assimilation, using existing assimilation algorithms within MIDAS. So that's the LETKF or the ENVAR. And we're starting with the LETKF because it's quite a bit simpler technically to implement. Depending on the grid you're using, it's much easier in LETKF because it only requires needing the ability to compute distances between observations and grid points. That's quite straightforward. Whereas ENVAR involves spectral transforms on Gaussian grids, so we would need to do lots of interpolation between grids. which could be a problem, especially near coastlines for an ocean model. So the initial tests, we used ensembles from the existing 20-member coupled forecast recentered on a deterministic state. So this is a really simple way. So we're using LETKF, which is supposed to be for ensemble assimilation, but this is a simple way for allowing to use that algorithm to actually produce a deterministic analyses. And now we're working on preparing the full system suite to enable daily cycling with the LETKF. So this shows the first example where we use the MIDAS LETKF for ocean assimilation. So only assimilating the in situ SST observations. We have on the top left the analysis increment using the LETKF. On the bottom left from the 2D VAR as used in the standalone SST analysis. And we can see on the right that it seems to be producing quite realistic looking increments. It's a cross section along this dashed line where we can see the warming at the surface corresponds to warming throughout the mixed layer, and then a slight cooling just below the mixed layer. So this, and we can see here, this is the analysis itself. So the mixed layer is located there. So it seems quite realistic and is consistent with the shallowing of the mixed layer in this region. So to take that as a starting point and move towards coupled assimilation, so a possible intermediate step would be to follow an approach similar to what Frolov proposed quite a few years ago, known as the interface solver, where essentially we still have two separate systems, but they're coupled in a much simpler way near the interface, and that would be done by well, the ensemble of atmospheric model integrations would use the SST ensemble valid at the initial time and hold it constant through the short-term forecast, whereas the ocean would be forced by this ensemble of atmospheric integrations. And then the same SST observations would be assimilated in both systems. And this would bring a lot of the benefits, maybe not all, but a lot of the benefits of coupled assimilation. So it allows to maintain a more realistic SST and therefore a skin temperature ensemble spread in the NWP assimilation cycle, and hopefully allows to make better use of these surface sensitive radiance observations that I mentioned. It's also much more flexible than a fully coupled data assimilation cycle, since both the model and the assimilation systems are still separate for the ocean and the atmosphere. So it would be, I think it would be much easier to make this as the next step before moving to a fully coupled system that relied on using the coupled model and coupled assimilation. So this just shows a simple diagram of how that would work, where we have ensemble information moving in both directions. So we have the atmospheric model run first, which then forces the ensemble of ocean models, and then the resulting ensemble of background states is used within the assimilation and also held constant during the next forecast, allowing the cycle to continue. So just to summarize what I've talked about, so I mentioned the increasing use of the MIDAS software for ocean sea ice, and I think that'll improve the efficiency of developing and maintaining data assimilation systems at our center for Earth system, for each Earth system component, while also making it possible to explore these future possibilities of coupled data assimilation. And the sea ice and SST analysis systems that I mentioned are already in MIDAS. The next step is moving towards a full 3D ocean ensemble ocean analysis using MIDAS. And I briefly described how the interface solver approach could be a nice intermediate step moving, again, towards fully coupled assimilation. Thank you.
Mark, we have time for questions. Do we have questions online? No? Okay. here. Yes, please.
Well, that was a lot of stuff. One of the things about sea surface temperature observations is there's a lot of observations. I mean, a vast number. And I did see at one point you mentioned the thinning. How much, I don't know if I should wait for Sergey's talk, but how much do you think you're going to be able to actually assimilate if you're going to do, are you going to take everything or how much are you going to throw away?
Currently, we are thinning the observations. So it's not only a matter of, in data assimilation, a matter of the being able technically to be able to deal with the sheer quantity of observations, but we typically do thinning also for NWP observations to address the fact that we think there's strong evidence that the observation error has horizontal correlations. And currently, most data assimilation algorithms cannot address that, cannot deal with that correctly in a mathematically correct way. So instead, what we do is coarsen the observations. We thin them so we don't have observations that are very close together and have errors that are very strongly correlated. So currently, we're thinning the SST observations, I think, at 50 kilometers in the experimental system. But I don't think it's a matter of technically we could deal with much more observations than that, than thinning at 50, but I'm very doubtful that it will likely degrade the results or have no benefit to the results because of this problem of enhancing the error correlations.
Okay, I mean, I think that the GHRSST would be shocked at saying, 50-kilometer resolution. So are you just basically saying 50 kilometers and that's it, or will you do some sort of like intelligent super orb or something like that as an alternative?
Yeah, there's a kind of super obbing we do, I think, right, Sergey? I think in the experimental system, we're not averaging the observations, but I think we're taking the median of the observations within certain area every 50 kilometers.
Okay, thanks.
Yeah. But it is a topic of active research in data assimilation, also for the atmosphere. How do we make use of the fine scale information from high resolution observations without being swamped by this problem of correlated observation error?
Yes, please.
Sort of a follow-on to that last question is I'm involved in dealing with uncertainties in these measurements, and one of the things that we've really begun working seriously on is error correlation, spatial and temporal. Not quite to SST at the moment. We've been concentrating on more the satellite data, but that will project into SST, and we started doing that. So my question is, if we were capable of providing you with spatial and temporal error correlation scales, which would be variable, of course, depending on the circumstance, would that help you?
It could help, but probably not in the way you would like. So it could help in terms of determining, giving a good estimate of how much we would need to thin the observations, which is not probably what you want. But eventually, yeah, as I mentioned, there is research in how to make use of this correlation information within the data assimilation algorithms.
Okay.
And I mean, we have a study from a little while ago where the idea was to assimilate the original coarse thinned observations in combination with what we call difference observations. So the idea of taking spatial differences between observations, because that really extracts the fine scale information while canceling out the correlated component of the observation error. So there's techniques like that. We haven't tried implementing it in like an operational system yet, but there could be approaches like this. And then the estimates of the correlations would definitely be helpful in designing those.
And my second question was related to you saying you assimilate an SST and you don't get spread, which causes you trouble. But any GRIS product comes with, in the case of a level 4, an analysis error term, which is meant to represent the spread from the creation of the level 4. So have you thought about using that number and having a little ensemble of the SSTs going into your ensemble on the basis of this estimate of the uncertainty?
It could be helpful, yes. But a big, so we, as I mentioned, we work a lot with ensemble data assimilation approaches. So it's not only the uncertainty, I think, that's important for SST, but it's how that uncertainty of SST is linked to uncertainty of the near surface atmosphere.
Right.
So a single sort of standalone estimate of uncertainty for SST wouldn't include that. We would need to include that in some other way. The ensembles would allow that.
Oh yeah, but I'm just wondering if there's a, you said this isn't really working very well. That would be a small step towards making it work a little bit better.
Yeah, for
when you're
sure.
Working on your more
Yes,
complex coupled system.
definitely. Thank you.
So we have time for one more question. Yeah. Yes, Andrea?
Thanks for the talk. Just have a question about how do you envisage coupled data simulation with the SST? If you have any plan to go towards coupled assimilation in, let's say, Radiance space and not SST. So to have really coupled observation operator, if you have any experience with that, and how this would interfere with the interface solver approach.
I don't think it would interfere with the interface approach. I think that it would be fine. I mean, so I think essentially what you're saying is instead of assimilating SST retrievals from satellite data, we would assimilate the reflectances or the brightness temperatures directly. Yeah, I think we haven't considered that yet for the observation types used directly in our current SST analysis system. As I mentioned, we already do that for the atmospheric radiance observations. So eventually, yeah, we would hope to do more, like for instance, AMSR2 may be a simpler, a lot of centers already assimilate AMSR2 in their NWP systems. It's used a lot for SST retrieval. So that would be, and I think it's included in the RTTOV radiative transfer package that we use for assimilation. So currently we assimilate AMSR2 as retrievals, SST in the SST analysis system. We don't use it in NWP, but if we were to assimilate it in the coupled system as brightness temperatures, then it would also provide information for the atmosphere, which we're not doing currently. So that would be definitely a good way forward.
Okay,
Yeah.
thanks.
Thank you, Mark. Thank you.
Okay. Thank you.
So our next speaker is Pallavi Govekar from Australian Bureau of Meteorology.
Hello, I'm Pallavi Govekar from Bureau of Meteorology. I work there with satellite science team, and I am involved with production of satellite SST products in the Bureau. So I am not ocean modeler, and this is presentation from Helen Bakes from the Bureau. Helen couldn't be here, and it's very late night in Australia now. So I am just presenting behalf of Helen here. So here, Helen and I would like to thank our Bureau and University operating colleagues listed here for their inputs for this presentation. So the Bureau uses the ensemble. Is it better? So the Bureau uses the ensemble Kalman filter system to assimilate data into our ocean forecast systems and future coupled NWP and seasonal forecast systems. Today, our talk will focus on current and new remotely sensed sea surface temperature products that we believe will have the highest impact on the Bureau's global and regional ocean models, currently based on MOM5 ocean model, and future global coupled NWP and seasonal forecast systems, which will use NEMO OCA 25 ocean model. All these models use Pavel Sokov's ensemble Kalman filter data assimilation system. Shown here on the left is ocean current speed from the new test 25-kilometer NEMO ocean model, and on the right from the 10-kilometer MOM5 ocean model. So the test NEMO ocean model is based on the UK Met Office GOS I9 configuration based on NEMO 4.4 with ERA 5 surface forcing. So NCAPC system provides a compact generic framework for offline data assimilation into large-scale layered models with NCAP. Ocean Maps V4.0i is the first global ocean forecasting system to employ and operationalize the NCAP system, resulting in world-class, world-leading performance. Observation assimilated into ocean maps on a 3-day cycle are satellite SLA and SST and subsurface ocean profiles from Argo plots, CTDs, gliders, and moorings. The next upgrade of ocean maps later this year will move to a daily data assimilation cycle and 7-day ocean forecast. So listed here are some SST missions currently operational or about to be launched in the next 5 years. Those shaded in dark orange currently provides SST data for Bureau's operational ocean models and experimental coupled NWP models. Those shaded in light orange are operational and being investigated by the Bureau for data assimilation. And satellite sensors shaded in blue will provide essential follow-on SST data for ocean models. So in 23, 4 satellite SST data streams were assimilated daily into Ocean Maps 4.0R, JAXA's MSR2 L2P SSTs, Nova Oceano's METOP B L2P SSTs, and Nova Star's VS L3U SSTs. Last November, we added METOP C SSTs, but these are assimilated every 6 hours, not daily as per METOP B. Prior to assimilation, all SSTs except AVHRR are bias corrected and only quality level 5 data are used. To reduce the number of observations per grid cell, MSR2 and VS SSTs are remapped to 0.04 grid cell and AVHRR SSTs are remapped to 0.1 degree grid. By averaging the good observations within each grid cell weighted with inverse error variables. All nighttime observations are used, but VS daytime observations during windy conditions are also ingested. All SST observations are assimilated with assumed error standard deviation much greater than the included in the L2P or L3U files to avoid overfitting. So in addition to polar orbiter satellites, SST data streams, the Bureau has investigated geostationary satellite SST data that has potential to improve regional accuracy in global and regional ocean models and coupled forecasts. So the Bureau produced real-time Himawari 8 SST products from 2016, but they were not sufficiently accurate to ingest into operational ocean models or SST analysis. So in recent years, we collaborated with the University of Reading and modified the method they developed to produce CCI SST climate data records for polar orbiting sensors. Using the new code, we have reprocessed IMOS Himawari 8 1 hour, 4 hour, and night SST composite products from 2015 to 2022 and made them publicly available. So the hourly Himawari 8 L3C that reprocessed data was tested by Bureau's Pavel Sako last year for ingestion into the Bureau's 2-kilometer regional ocean model. And he found little impact on overall performance. However, in cloudy regions like in the maritime continent, it is expected to improve performance closer to the coasts. We decided that the Bureau's system used to reprocess Himawari 8 SST data should be improved for Himawari 9 to reduce the noise further. So the Bureau's ACS bias model used for reprocessing Himawari 8 grease products was updated this year prior to reprocessing Himawari 8 and 9 data. New terms were added to the definition of the model and a new fitting algorithm also was used. Matchups with drifting and mood voice SST data under well-mixed condition and for all quality levels indicate that the new bias model is significantly less biased. With the reprocessed Himawari data, we noticed that the Bayesian cloud masking that we use was stringent and was flagging some clear pixels as cloudy. So recently with University of Reading, we have modified the code for Himawari 9 based on the latest ISA CCI SST version 3 code and new lookup tables for Bayesian cloud clearing. A new version of the radiative transfer model and better tuning to Bureau's NWP model output. So we will be using all of these things for new pre-processing for Himawari 9 and Himawari 8. So left-hand side here is showing the previous reprocessed data coverage we were getting, and the right-hand side showing the improvement with the new method. So here we are showing a difference between the pixel of being clear by two methods. So at the left hand side, it's showing the old method, and the right hand side shows the middle one shows the new method, and the right hand is the difference. So we are having pure clear SST pixels are now identified as cloudy using new method. So we are able to get about 40% more data with the new method now. The data is processed for Himawari 9 from October 22 to September 23 and is available from NCI on request. And we are looking forward for producing a real-time Himawari 9 by June 2025. So in summary, the Bureau is currently assimilating 5 SST data streams via the NCAP system into operational ocean models and coupled NWP models. NOAA 21 VSL3U SSTs will need to replace Suomi MPP VS SSTs in ocean models and test coupled systems in this coming year. We expect the new Himawari 9 SSTs with improved cloud clearing and bias model to improve the Bureau's regional ocean models, especially within 15 kilometers of coast, which micro EMSA2 SSTs cannot sample. The future higher resolution microwave SST products from EMSA3 and CMR may also benefit Bureau's models in the future, and in partnership with the UK Met Office, the Bureau is moving forward global coupled NWP with ocean data likely assimilated using with NCAP system. So thanks for your time and attention. Question time.
Thank you, Pallavi. We have a couple of minutes for questions. Yes, please.
You have shown the improvements with the new bias correction versus the older bias correction. So I'm wondering the detail, what kind of bias correction you applied for the new method in compared with the older method?
So this one, right?
Yeah.
Yeah, so the old bias model that we're using was initially developed for AVHRR since the polar orbiters in the Bureau, and it was only focused on Australian region. So we use it as it is to Himawari 8, and then we reprocess the data, but then we realized that there are big biases, like here, there were day and night discrepancies, and then also the hemispheric differences. So on the right hand side, now we changed the time. So because we were using it for AVHRR, the equatorial crossing time was always same, and unintentionally when we changed it to Himawari 8, it was representing only one time instead of the whole 24 hours. So we have to change how we use time in our bias model, and then we have to add some latitudinal changes also to get northern and southern hemisphere tuning correct. So now with the new bias model, we don't have that day and night discrepancies, and we have significantly reduced the bias.
Okay. The other question is, when you're showing the Himawari 9 versus 8, but using the Himawari 9, you're also seeing the new method. So I'm asking whether how much actually the improvement is caused by the new satellite or by the new bias collection method, or how you separate with them? Can you?
So yeah, it just because Himawari 8 data was reprocessed with the old method and Himawari 9 was with the new method. I'm showing the differences. But then, yeah, if I use same method for Himawari 9, then I will see the same differences.
Thank you again, Pallavi.
Okay.
It's my turn now. Yeah. Dorina yesterday and Mark today, this morning, have already mentioned that we are working on a new global daily SST analysis system. And we all know that nearly all NWP centers nowadays have been producing real-time SST for almost 40 years, right, since Reynolds and MC SST product. And at Environment Climate Change Canada, we also have a system that runs for years. So why to develop another system? And in this presentation, I'll explain the reasons of doing this. And I also would like to acknowledge our two colleagues that work with Mark, Dorina, and I. It's Alain Kaya and Yves Frankengeto. So this is the outline of the presentation. First of all, I would mention the motivation in developing a new system. Then it will be a brief overview of the elements of it. Then we see the results of the comparison between the current system and the new system, and we move to conclusions and the SST outlook in a future coupled data assimilation approach. Our first try to compute coupled data assimilation was already 5 years ago, and you see here on the left the scheme of the system. It was built on two separate deterministic atmospheric and ocean data simulations that communicated with each other using a coupled ocean atmosphere CIS model. And you see that every day the system, the coupled forecast were restarted from an uncoupled standalone current SST operational analysis. But nevertheless, this system provides some small improvements of the atmospheric and ocean scores, but really small. And an example of such improvements here on the right, it's a position of a hurricane near the Florida coast. Is computed by the ECMWF operational analysis here in a black contour, and the red contour is our new weekly coupled data estimation, which is a little bit closer to uncoupled data simulations, the hurricane provided by the uncoupled data simulation, but the difference was really small. So the performance of the weekly coupled data simulation was suboptimal, and it was claimed at that time that to make it better, to perform better, it should be ultimately cycled. The SST initial conditions should be ultimately cycled within the common data assimilation framework along with the atmosphere, ocean, and sea ice. So our motivation to develop a new SST analysis arises from the initiative to advance coupled data assimilation. And as Mark mentioned before, many people at Environment and Climate Change Canada work on MIDAS, and we decided to put the SST analysis also into MIDAS. It provides several benefits because we can use existing elements of data assimilation, and when we can start first to develop standalone SST analysis, then we can easily cycle all these elements to apply them into the 3D ocean data assimilation standalone first, and the coupled data assimilation further. So it provides an easier transition to coupled data assimilation. And by the way, MIDAS provides a faster and computer environment, and it's more flexible than the current operational system. Like for example, we can easily change the resolution of the analysis, or we can easily add some new data. So that's why our motivation to replace eventually the current operational SST analysis. The MIDAS-based SST is built on 6 independent programs. The first one is a key, is computing the analysis of the SST. The second one computes the satellite SST data bias estimations. The next program computes the background check and special thinning. Then we also insert synthetic pseudo observations into the ice-covered areas. We compute the background state because we don't have any numerical model. and we also provide analysis error. The data assimilation method used in MIDAS SST is incremental variational 2D-var, where the background error covariance matrix is computed using correlations modeled using a diffusion operator. And in the current implementation, the correlation length scale is set to 50 kilometers globally. And we compute the global analysis on two grids, rotated grids that we call them yin and yang, as it's done in our NWP model. This allows us to avoid the problem of computing the diffusion operator on numerical poles. The next program is to compute the background check. The background check is based on the comparison between observations in the background, and it's done for all type of observations in the same way, but the rejection level is normally similar to what is used in our NWP systems, but we have an exception for satellite data that are acquired on the lakes. Sorry. This is an example of these Canadian lakes. You see, these shallow lakes can have a large and sudden gradients during the day in spring and early summer, and by using a much more permissive criteria for selection, we keep good data to update properly the surface temperature on these lakes. And the thinning is followed by the background is followed by the thinning, and you see the difference between the operational system that they use latitude band dependent thinnings, spatial separation. But we in MIDAS, we have it constant. It's around 50 kilometers globally, and by doing this, we have data that are retained for assimilation that are evenly distributed over the space. The next program computes the bias for satellite data. We use the similar approach that is employed in the current operational system. So we suppose that in situ data are unbiased, and we compute the bias for satellite data with respect to in situ data. But we use completely different method of computation. In the operations, it's another data assimilation technique that is used to estimate bias. So they compute the collocated differences between in situ and satellite data, and they assimilate this difference into this system to compute the fields. We do like a simple approach. We first put all the data in situ and satellite separately for day and night on a grid, using a small search radius of 25 kilometers. And then we compute the differences between satellite and in situ data by averaging them using a much larger search radius, which is 1,200 kilometers, to compute the smooth fields. And the final product is a linear combination of the current bias estimation and the previous bias estimation from previous day. And if we have a look at an example of bias estimation produced for METOP B night data for some particular day in the operations, and the same estimations for produced by MIDAS, we see that generally the spatial patterns are similar, except maybe this area in the south, when the operational system provides biases in the areas that are too far from the actual locations of in situ data. In these locations, we do not compute the bias in MIDAS because we compute the bias only beyond some smoothing distance, which is in our case only 1,200 kilometers, and after that it's put to zero. So this slide summarizes the similarities and the differences between the two systems, the new and old one. And So we practically use a new data assimilation technique to compute the analysis, to devar instead of optimal interpolation. We assimilate the same set of data. The grids are different, but the final product is of the similar spatial resolution of about 10 kilometers. So we produce in both systems thinning, we produce the background quality control, and using in the same way we produce the background state using relaxation towards climatology. It's especially important because we don't have any numerical model, and we update, by doing this, we update areas that are not observed. And these are results of comparison between the new and the old system. So we did two experiments of 2 years using MIDAS, and which is in red, and the operational system in blue. And here we see the mean bias, the evolution of the mean bias in the North mid-latitudes region. And you see that MIDAS produces smaller biases. As for the standard deviation, it's similar. There's no statistically significant difference. But these data were assimilated in both systems. But this is a comparison against independent Argo data that are not assimilated in our systems. And we see the same pattern. MIDAS provides smaller biases than the operational system most of the time. And it's similar standard deviation. And if we compute the differences between the MIDAS and the current operational system analysis for the summer here on the left and for the winter on the right, we see that the biggest discrepancies are here exactly where the bias estimation techniques perform differently. So when the operational system provides some bias estimations, we don't have it in MIDAS, so we have this difference. And we also have some discrepancies on the lakes. Is due to our differences in the thinning and then background quality control, and the way how we insert synthetic the observations in the ice covered areas. And we also tested the new and the old system within the deterministic global prediction NWP system and the deterministic ocean prediction system, and we obtained nearly neutral impact when using a new system with respect to the old system, which is a good news for us. And finally, some words about the role of SST analysis in the future coupled data assimilation approach. Well, of course, we can extract the SST from a surface layer of a coupled ocean atmosphere model, but only for the ocean domain, right? If we have some lakes, which is important for local weather prediction, it can be important to keep SST standalone analysis for these areas, even in a coupled data assimilation approach. And these are my conclusions. So we implemented a new global daily foundation SST analysis using MIDAS system. The new system provides smaller biases than the current operational system, and but the differences between the two systems are so small that it provides near neutral impact on NWP and ocean prediction systems. But by implementing MIDAS, we're getting close. MIDAS-based SST analysis, we're getting closer to the fully coupled data assimilation systems. And our next steps during the operational implementation is to test the new system within the high-resolution Canadian regional system to see how the system performs, like especially using the differences on the lakes and so on, and also to see impact on coupled medium-range forecasts. And finally, I would like to draw your attention to our paper, which was actually accepted yesterday. And this paper contains all the details about the new system. Thank you.
Sergey, and then you have there's a question from the online.
Okay, maybe one because we.
Do you have from the FRIP? Do you have any plans to have the spatially temporally varying correlation length scales?
Right now, we only seen the data, so we especially separate them, so we suppose that are not correlated. This is the only way right now, but yeah, there's no concrete plan to do this.
There's someone. Sorry, who is raised hand and Heron. Okay, Heron.
Yes. Hi. Thank you. Interesting talk. I look forward to your paper. I was puzzled. You mentioned under a bias estimation of in situ data that you don't do any for the new system, but for the operational old system, you use ship data only. I didn't catch, what was that in relation to? What do you actually use the ship data for, please?
We don't correct the in situ data, the ship data, do not correct them neither.
Right, but you do in the operational SST analysis, do you?
And we only do the background check for all the in situ data as for other data. If they are really out, so they're just rejected. But if not, they are directly assimilated.
Right. So what do you do in the current operational SST analysis? You assimilate the ship data with bias correction or without?
I think that it's a quite complicated procedure in the current operational system. So they do something with this with a special treatment of the ship data. They sometimes reject the data for some particular regions for some reasons. At that time, it was maybe thought that it should be more secure to reject some data. Well, a lot of like manual treatment, manual tuning, but in MIDAS we don't do that.
Okay, thank you.
Thank you. So we should move on, I think. Our next speaker will be online.
Actually, could I ask one question? I've been standing here for you.
Okay, go on.
Okay, yeah, I enjoyed your talk. With this model simulation, I'm wondering if you've considered assimilating ocean heat content type of products to improve your ocean dynamic, ocean heat exchange estimates that you look at when you use DSST, because they're all very much correlated.
Well, it could be possible, of course, but right now we are just assimilating exactly the same observations and adding the observation that will feed the operational system. And when this system will be operational, it will use some fixed set of data. But for scientific reason, of course, we can play with different sources as well.
Yeah, altimeter data can be very useful in those kinds of processes for ocean heat content estimates.
Thank you. So let's move on. Our next speaker is Browne from ECMWF. Please.
Hi, everyone. Can you hear me all right?
Yes.
Excellent. Right. So, yeah, sorry I can't be there with you in Montreal, but thanks for making it possible that I can present online. And it's a really good session to be in. So great to follow Mark, who's basically set up all the motivation for this. And Andreas Stortos asked exactly the question to Mark, which I'm going to try and answer in my presentation. So talk to you about how we're doing radiance assimilation for SST and sea ice concentration here at ECMWF. One of the main things to do in my presentation is to tell you that Tracy Scanlon has an excellent poster with much more detail about what we're doing, so specific details about microwave. So if anything in this presentation is of interest, make sure you check out Tracy's poster and then speak to her. So what I am interested in is really how are we going to do coupled observation operators in 4D VAR, so in a coupled 4D VAR. So I'm going to start off with a few slides of equations. A lot of people balk at these equations, but it's kind of there to show you that things simplify and we can get something nice and easy sort of structure to assimilate these things in a coupled 40 var. So 40 var, basically we start with a cost function, and it has the cost function J. It has two terms, a background term and an observation term. So if we're coupled, then under certain assumptions that all the pieces that go into this 40 var, if they're of the right structure, so block diagonal things and things which are separable, then that whole cost function is separable. What that means is that in a coupled system, we can solve two separate minimizations, and the solutions of these minimizations will give us a solution of that one coupled system. So in this case, we have x1. For our purposes, x1 will represent the atmosphere, and then x2 can represent an ocean. So what we do is we have a coupled system at ECMWF where we have separate minimizations, atmosphere and ocean, and we bolt them together. And this is how we produce our CIRA and CIRASAT reanalyses. So yeah, this is the setup which we're in, but we really want to take this a bit further and say, right, we have observations, which are incredibly important. That's why everyone's in this room. And they're basically coupled observations. So you have an observation operator, which is not just a function of the atmosphere, and it's not just a function of the ocean, it's a function of both of them. So how do we include these properly in this coupled system? But importantly, we want to keep separate minimizations. So Mark was talking about getting all the way to coupled, strongly coupled DA. I don't want to be so bold as to push all that way. So what can we do by keeping our separate minimizations? So what essentially we would like is we would like to include some coupled observation term, which is a function of both our atmosphere and our ocean, and they would have to go into the observation term of our cost function. So how do we do this? What do we do? So what we do is we introduce some intermediate variable. I'm going to call it an extended control variable, XCV. So we're going to extend the control variable. This is kind of going to be an atmospheric concept, but that doesn't really matter. So we're going to extend our control variable, and that control variable is going to be some function of our ocean state. So for the time being, don't worry about what that function is. We'll get to what properties that function will have to have. But if it is some function of our ocean state, then what we want to do is we want that to basically be able to plug into our observation operator so that we have a slightly different observation operator, but it's the same thing as using the whole ocean state. We can just use this extended control vector in a slightly different observation operator and get the same observation equivalent. So if we can do that, then we can realize that our observation term, which was a function of atmosphere and ocean, can now be reduced to something which is an observation term of the atmosphere and this extended control variable. And then, okay, so we've reduced that. So if we, as the name suggests, extend the control vector in our atmosphere to have all our atmospheric variables and this extended control variable, then we basically are able to just give these coupled observations to our atmosphere. And our atmosphere will then minimize over both the atmospheric state and the extended control variables. It will produce the state that we want there. But then the question is, this is the atmosphere. We now have a disconnect between our atmospheric state and our ocean state. So what we have to do is we had to add another term to our ocean cost function, which will be this term on the right. So this JCV term. And the idea of this JCV term is it has to penalize the misfit between what our atmosphere is going to fit as our control variable and what the equivalent when we use this mapping F of our ocean functions gives us as this control variable. So in the variational world, we need to give this some covariance matrix. What covariance matrix it is will depend on exactly how we define our extended control variable. And there's a few different options. I'm not going to go into that too much, but you'll see one in a second. If I'm running on too long and going to stop you guys from getting coffee, please shout at me and I'll hurry up. So we basically, the idea is we extend our control variable and we add this penalty term to our ocean state. So the mapping that we introduced, what properties does it have to have? Well, we want to be able to solve our minimization. So we need a derivative. It will look like this. And the important part is here. So we need this gradient term to exist, which basically means we need to have the adjoint of our mapping F available. That's not too onerous if we're in variational DA world, but we need to know what that is, and thinking about it helps us. Then one thing which I'll just talk about today. So if our extended control variable is defined in the observation space, then the JCV term, which we give to the ocean, essentially is just adding additional observations to the ocean, so that F becomes essentially an observation operator, a nonlinear observation operator applied to our ocean state. And in that case, then we can use the infrastructure which we have to for our observation error covariance model, and basically put that in as our covariance model, which we want to use for our JCV term. So that's good, because in that case, we have all the infrastructure that we need to actually do this. So a little bit more of concrete now. What can we do about these mappings F? So the first example is for SST related things. So our extended control variable, what we use is the skin temperature. So basically in the atmospheric world, we have a skin temperature, a concept of skin temperature. And we then have to know, how do we map our ocean into the skin temperature? That's what we do at ECMWF in the coupled system, is basically take our top model level from our ocean state and add the cool skin correction. And that's all we do to get to our skin temperature in the model. So if we do that, we want to think about what are the those conditions which we had on it. So we needed to look at the adjoint, which means we need to just check the derivative of this with respect to our ocean state. And what was really nice for me is that I computed this and found that the derivative with respect to the ocean, like the ocean state, is almost zero. It's so close to zero that we can safely approximate it as zero, because all the other approximations in the system are substantially like larger errors than this would be. So to use this in our ocean state, we can essentially use the same Jacobians as we would use for a observation of SST, and that will give us to almost machine precision exactly what we should be doing, accounting for the cool skin correction, which is great. So this extends not just to SST, but we can look at sea ice. And in that case, we have our extended control variable just as the total ice concentration in a grid box, in which case there's no corrections, and we can use, we have all the Jacobians that we need to assimilate that. And then interestingly, we also have a project looking at altimeter assimilation in the coupled system, and in which case what we do is we just pass our sea surface height from our ocean model, and then the rest of the things which go into it are purely atmospheric corrections. So our Jacobian there of this is zero. So we can use this directly to get to assimilate altimeter return times, which is really quite cool. So to go back to how does this look when we're actually trying to assimilate radiances for sort of, in this case, infrared radiances, we can look at the increments which we get in this whole coupled system using this framework I've just described and look at the increments. So these are incredibly similar plots to what Mark showed, but in a different location. So we can basically see that this case I'm showing on the left, the top model level temperature increments in the ocean, and you can see where there's missing data. So this must be from a set of infrared sensors. So where the clouds are, we're not getting any information into the ocean. And then if we look at a section through the tropical Pacific there, and we look down into the ocean, we can see that we get increments from these brightness temperatures down to almost 70 meters in some places. The stuff below that is information coming from either altimeters or the in situ, the moored buoys, or some maybe Argo float that happened to be there in this cycle. So the main point of this is that it works, and from the brightness temperatures, we're getting these increments all the way through to the deeper parts of the ocean. So to whet your appetite about Tracy's poster, she's looking at assimilating the microwave data, and she has some really nice results where her new microwave channels that she's assimilating are correcting the positions of tropical instability waves in the Pacific. So you can see the peak of the wave was here, and it shifted westwards when we're assimilating the new microwave data. So go and see our poster, please. Then also, just to say, we can do this for the sea ice concentration as well. So just looking at AMSR 2 brightness temperatures. What's really nice is we see nice increments around the sea ice edge, where the data is basically giving us our faster updates. So the observations are more up to date than our model was. So the ice edge is being corrected. And this also kind of shows you that we're missing some sectors in these increments. So the fact that we're not using global level 4 data, which up until now is the sort of thing we have been doing. This is quite new for us to be able to go to this low level data in the coupled system. Okay, so to wrap up before coffee, go and see Tracy's poster because it's got some really interesting stuff in there. Yeah, I've basically showed you this coupled framework, and it's quite simple, and it fits into the variational DA framework quite nicely and tells you exactly what you need to do. We have to tune this system. It's not without a tuning exercise. So I've not showed you long runs or anything. I just wanted to show you that it's possible and we're working on it. Yeah, and hopefully it will be operational soon, subject to it performing well. And we can do lots of stuff, not just SST. We can do sea ice and altimeters and hopefully other things later on. So just finally to tell you one thing, which is hot off the press, is that even before implementing this, we having some research experiments, basically verifying this against the ocean in situ data, has shown that we're doing something wrong with some of our hyperspectral infrared. And it seems that we're aliasing some ozone increments into skin temperature increments. And we wouldn't have known that if we hadn't have put it into this coupled system and seen what the in situ ocean was telling us. So it's pretty powerful. So hopefully we'll learn a lot more in the future. So thank you very much.
Thank you, Philip. We have time for one quick question. Yes, please.
Thanks, Phil, for a very nice talk. And even though I may need to digest a bit the formalism, my question is about you stress the separate minimization. So I'm curious if having, for instance, if you tried with high frequency SST data and you have 4D VAR in the atmosphere and 3D VAR in the ocean, this leads to any inconsistency or is negligible issue?
It's going to be an interesting one. So we've not yet been able to try with 4D VAR in the ocean, but hopefully when we get the geostationary infrareds into this system, hopefully it will work. But potentially if we have a lot of data throughout the window, then we might gain a lot from 4D VAR over 3D VAR. But we will take a practical approach, and we will have to thin the data initially to make it work. But yeah, that's exactly the sort of things that we're hoping to find, and hoping that they're not a problem, but expecting that we might see some things to worry about.
Okay, thank you.